Euler's identity is considered by many as an equation that shows the beauty of mathematics. These seemingly unrelated mathematical concepts come together in this simple equation. Why is this equation true? More importantly, how does it show the beauty of mathematics? Let us go on a journey through time to answer these questions. We begin our journey in South Africa in the year 41,000 BC. We live in a village where we haven't developed the concept of numbers, but we describe quantities in our everyday lives. The number of people, the amount of food, and so on. But what if we wanted to track something intangible, such as the number of days that have passed? When a day goes by, we'll mark a line on this piece of animal bone. This is the oldest mathematical artifact that scientists believe is a tally of the number of days, acting as a sort of primitive calendar. Fast forward about 40,000 years as we enter the ancient world. Societies have developed with population numbers in the millions. There have been major advancements in agriculture and construction, and using a tally system is no longer feasible. Instead, a quantity is represented by a symbol or a number. There is evidence that the ancient Egyptians even had symbols for fractions. These symbols can be thought as the precursors to the natural numbers and rational numbers that we are familiar with today. During a similar time period, ancient Chinese mathematicians have developed a different number system. Colors have been used to differentiate between these normal numbers in red and these so-called negative numbers in black. Historians believe that these negative numbers were used for balancing financials and calculating debt. By extending the normal numbers with negative numbers, we get what we now call integers. The symbols or numbers developed in the ancient world can be represented on a number line, where we have the normal numbers representing quantities extending to the right, negative numbers in the opposite direction, and we can even find, or at least approximate, fractions on this number line. Interestingly, every single number on this number line can be built by the numbers 0 and 1. If we start at 0 and continuously add 1, we can build the natural numbers. By continuously subtracting 1 from 0, we extend the natural numbers to the integers. And by dividing combinations of integers, we can construct rational numbers. In other words, 0 and 1 can be thought as the building blocks of numbers. Ancient Greece had a unique view of mathematics compared to the rest of the ancient world. Not only was it a way to understand the world around us through the study of geometry, but it was thought to be a divine process in understanding truth. To get to a truth, a series of arguments that had a logical conclusion had to be laid out, known as a proof. One issue is to test the integrity of a proof. We must question each and every argument, potentially leading us to a never-ending list of arguments. To work around this, we'll go down the chain of arguments and stop at one point and simply make an agreement that this is just assumed as a fundamental truth. These assumptions are known as axioms. For example, let us assume that the angle in a straight line is 180 degrees, and the alternate angles in parallel lines are equal. By drawing a triangle and constructing a line that is parallel to one of the sides, we can lay out a proof and make the conclusion that the angles in a triangle add to 180 degrees. The ancient Greeks made fascinating discoveries, such as one astronomer who calculated the distance of the Earth to the Moon with remarkable accuracy. Another piece of work by the same astronomer was to create a table of chord lengths in relation to the subtended angle. In essence, this table was describing a manipulated sine ratio, which is why he is often referred to as the father of trigonometry. Triangles with the same angles are called similar triangles, where corresponding sides have the same ratio. Because of this, notice that the ratio of the sides within the same triangle will be the same across all similar triangles. This is why the trigonometric ratios are consistent for all right-angled triangles that are similar. Now the question is, what is the actual ratio value? For some angles such as 45 degrees, we can geometrically find the ratio with the help of a famous theorem discovered by another ancient Greek mathematician. But for most angles, the ratio is not so obvious. We will see how we can approximate these ratios later in this video, which coincidentally is integral to the proof of Euler's identity. For angles greater than 90 degrees, mathematicians have visualized the triangle in a unit circle, where the hypotenuse is always 1. Once the angle passes 90, the triangle is reflected, and the same ratios apply. Same process of reflecting the triangle is applied once we cross 180. And 270. From this, we can visualize the sine function and the cos function. And this is how we get the periodic nature of the trigonometric ratios. Notice that sine 180 is 0, and cos 180 is negative 1. You are probably familiar with the relationship between the circumference, or area of a circle, to the radius, where pi is a fixed value for all circles. There is evidence that ancient mathematicians had this understanding as well. The Babylonians came up with an estimate for pi, as did the Egyptians, which are pretty good approximations, but not quite accurate. One of the complexities in calculating pi is the difficulty in measuring the properties of a circle accurately. This changed when one Greek mathematician came up with a geometrical approach for approximating pi. He argued that the area of a circle can be estimated by inscribing a regular polygon. By increasing the number of sides, a more accurate estimation can be found, which can be used to estimate pi. Notice that if the radius is 1, then pi is equal to the area. The advantage of this approach was that straight lines can be constructed, which are much easier to work with, and only one slice of the area is needed. He began with a regular hexagon, where this angle is 60. Because the side lengths are equal, this is an equilateral triangle. By defining the radius of the circle as 1, the height of this triangle can be found by Pythagoras' theorem, and therefore the area can be found. The number of sides was then doubled to 12. The area of the hexagon was just found, so only the area of these smaller triangles need to be found. The base of the triangle is half of 1, and the height is 1 minus h. The area of this small triangle can be found, and therefore the area of the polygon. The same process was applied to polygons of sides 24, 48, and 96 to get an estimation of pi. No matter how many sides there are, the polygon will always have an area less than the circle. So we then drew a polygon that circumscribed the circle. By using a similar geometric approach, and realizing that this polygon always had an area greater than the circle, a remarkable estimation of pi was found. This was a fascinating approach, however it is not 100% accurate. In fact, no method of estimating pi can be 100% accurate, as pi is an irrational number, where it cannot be represented as a fraction of two integers. In other words, the decimal digits of pi are endless. Pi is revealed in many different areas of mathematics. One way that pi is used is related to the measurement of angles. Most people use degrees, where one full rotation is 360 degrees, but there is another measurement of angles called radians, where 2 pi radians is one full rotation. This is a very natural measurement of angles, as pi is closely related to the properties of circles. For example, if the radius is 1, then the angle in radians is equal to the arc length. So instead of using degrees, we can say that the sine of pi radians is 0, and the cos of pi radians is -1. Mathematicians in India made fascinating discoveries, such as the Pythagorean triples, approximations for the square root of 2, and some of the trigonometric identities. One important development was their number system, which was later taken by Arabic mathematicians and spread to Europe and the rest of the world. This number system is known as the Hindu Arabic numerals that most of us use today. A Persian mathematician who studied at the House of Wisdom in Baghdad is known to be responsible for the spread of the Hindu Arabic numeral system to the Middle East and Europe through his writings. The same mathematician also discovered the idea of balancing equations. This concept is now known as algebra, and is why he is often referred to as the father of algebra. Algebra is an efficient method of communicating mathematical ideas, where symbols are used for unknown values, and we can manipulate equations as long as both sides are balanced. Before algebra, a problem would have been written. The area of a square is 4, then the side length of the square is 2. The algebraic representation of this would be x squared is equal to 4, therefore x is equal to 2. Not only is algebra a convenient way of communicating mathematical ideas, but it separates mathematics from geometry. This expression can be algebraically manipulated into a function, and by drawing the graph of this function, we can see that there is in fact another solution, -2. This second solution would be impossible to find if we were bound by geometry. However, algebra had its limitations. You are probably familiar with the quadratic formula, which is used to find the solutions of quadratic equations. However, there is a problem where for some equations, we are left with the square root of a negative number. This is an issue as any number multiplied by itself will always give a positive number. An Italian mathematician in the 1500s faced a similar problem while solving the cubic equation. He came up with a general solution for some cubic expressions, where he encountered the square root of negative numbers. He concluded that a solution involving the square root of negative numbers does not exist and dismissed this concept entirely. Shortly after, another Italian mathematician provided a different perspective. He argued that the square root of negative numbers is a category beyond the real numbers and should not be dismissed. This was a fascinating realization, as he was able to pick up where his predecessors gave up and was able to find the missing solutions to the cubic equation using this new category of numbers. Square root of negative 1 is now known as the imaginary number and is a component of complex numbers. The square root of -1 does not lie anywhere on the real number line. This means that the real numbers can be extended with the imaginary axis in the positive direction and negative direction to build what is known as the complex plane. A complex number is a point on this complex plane with a real component and an imaginary component. The advantage of this approach is that a point on this 2D plane can be represented by a single number. We can perform operations on these complex numbers where I can be treated just like any other variable. But since I is equal to the square root of -1, any instance of I squared can be replaced with -1. The distance of a complex number from the origin is known as the modulus, and the angle between the modulus and the positive real axis is known as the argument. From this, a complex number can be represented using the trigonometric ratios. Notice that if we assume the modulus to be 1 and set the argument to pi radians, the imaginary component, or sine pi radians, is equal to 0, and the real component, or cos pi radians, is -1. And this is consistent with what we have already discovered. Despite its name, imaginary numbers can be found in real-life applications, such as quantum mechanics and electrical engineering. Jump ahead to 17th century Switzerland, where a Swiss mathematician was studying wealth and compound interest. If there was $1 in a bank account that paid 100% interest per year, how much will be in the account after a year if the interest is applied once? Start with $1 and 100% of that dollar is added once, so we are left with $2. What if the interest was applied twice within the year? Again, we start with $1, but this time half of the interest is applied first, then the other half of the interest is applied again. Now what if the interest was applied every month? Start with $1 and the interest divided by 12 is applied 12 times. You can probably see the pattern, where n is the number of times interest is applied. With this, we can easily calculate our return if interest was applied every week. Notice that as n increases, it seems like the result is approaching a value. This value is the constant e. As n increases, we get a better approximation of e, and with the luxury of computers, a decent approximation of E can be found using this formula. However, the first calculation was performed by Leonhard Euler. He proved that this constant can be represented by an infinite sum, and was the first person to define and calculate E. This value is now called Euler's number, and is another example of an irrational number alongside pi. Interestingly, Euler's number is an irrational number that is not based on geometry. Pi is a constant that arises from the properties of circles. Root 2, another irrational number, can be geometrically represented using Pythagoras' theorem. And we have Euler's number, an irrational number found from compound interest. The function e to the power of x has some interesting properties. The value of f of x, or the y value, is equal to the slope of the tangent at that x value. The area under the curve is also equal to the y value and the slope of the tangent. This is a unique property that cannot be found in any other function. Euler's number can be found in many different areas of mathematics, such as statistics and the study of growth and decay. During the late 17th century, there were major advancements in mathematical ideas. And during this time, we have two notable mathematicians tackling two problems independently, but arriving at the same solution. Calculus is made up of two primary components, where differential calculus is focused on the rate of change. The rate of change or slope of a straight line can be found by taking 2 points on the line and calculating the rise over run. But how can we find the slope of a curve? We take a similar approach of taking 2 points on the curve, then calculate the rise over run. But we decrease the value of h to get a more accurate value for the slope. The idea is that we take the limit of h going to 0, and we are left with the slope of the tangent at this point. This process of finding the slope is known as differentiation, where this equation is known as the derivative. There are various rules of differentiation, such as the constant term rule, where the derivative of any constant is 0, the power rule, which states that for a function such as 5x to the power of 4, the derivative is found by multiplying the function by the exponent, then reducing the exponent by 1. The chain rule, which for our purposes we just need to understand that a function such as 4 times 2x plus 1 to the power of 3 can be differentiated by treating the inside of the brackets as x and applying the power rule. So we multiply the function by the exponent, then reduce it by 1, but then we also multiply by the derivative of the inside of the bracket, which is 2. The sum rule states that if we have a function such as the following, then the derivative is found by differentiating each term. So the first term would be 0 by the constant term rule, the second term can be found by the power rule, and the third term can be found by the chain rule. Notice that we can continue differentiating a function to find the second derivative, third derivative, and so on. As previously mentioned, the slope of e to the power of x is e to the power of x. This means that the derivative of y equals to e to the power of x is e to the power of x. The sine and cos functions also have an interesting property, where the derivative of y equals sine x is cos x. The derivative of cos x is minus sine x, then minus cos x, and back to sine x, and it continuously cycles. Integral calculus is focused on accumulation, or finding the area under a curve. We won't be diving too deep into this aspect of calculus, but the idea is that by drawing rectangles under the curve, we can find an estimation for the area by taking the sum of the areas of the rectangles. By letting the number of rectangles approach infinity, we get a more accurate value of the area. This process of finding the area is known as integration. The amazing breakthrough was the discovery of the fundamental theorem of calculus, where it was shown that differentiation and integration were inverse operations, just like how addition and subtraction are inverse operations. Building on top of calculus and other mathematical ideas developed throughout history, we have an English mathematician who formalized a concept known as the Taylor series. Say you have a function, and you want to calculate the value for when x is 0.2. If you were given a pen and paper, how would you actually calculate this value? Let's assume that you could express a function as the following infinite series, where the function is centered at x equals a. Then all we need to do is find the values of these constants. We can use the rules of differentiation to find the first derivative, second derivative, and so on. Notice how if we calculate the function for when x equals a, then all these terms would be 0. And therefore c0 would equal to the function at x equals a. c1 would equal to the first derivative at x equals a. c2 equals the second derivative at x equals a divided by 2, and so on. In other words, c of n is equal to the nth derivative at x equals a divided by n factorial. And if we plug these values back into our original series, we are left with what is known as the Taylor series. For a function such as sine, deriving the Taylor series expansion can be relatively straightforward. For example, if we take the center, or a, as 0, we know that sine 0 is 0. The first derivative is cos x, and cos 0 is 1. The second derivative is minus sine x, and again sine 0 is 0, and so on. Once we simplify this out, we are left with the Taylor series for sine x. Now we are able to approximate the value of sine of 0.2 radians. Using a similar method, we are able to derive the Taylor series for cos x and e to the power of x. As you can imagine, the more terms you calculate, the more accurate the Taylor series will be to the actual function. Graphically, this can be shown for the sine function, where this is the graph for 1 term, 2 terms, 3 terms, and so on. Our journey began in the ancient world with the primitive tally system and the precursors of the natural, rational, and integer numbers. In ancient Greece, we introduced the axiomatic method, trigonometry, and discovered pi, an irrational number. Later came the Hindu-Arabic numeral system, the birth of algebra, and the discovery of the imaginary number. In the 17th century, we have the discovery of Euler's number and the invention of calculus. Our final stop lands us in the year 1748. Leonhard Euler published a book titled Introduction to the Analysis of the Infinite, and in chapter 8 of his book, Euler further explores the Taylor series expansions of the trigonometric and exponential functions. He took the expansion of e to the power of x and substituted x with the imaginary number I multiplied by x. By simplifying this out and realizing that I squared is minus 1, I cubed is minus I, and so on, he was able to simplify the equation further. By grouping the right-hand side with the real components, or terms without an I, and the imaginary components, or terms with an I, he was left with the following. By realizing that the real component was the Taylor series expansion for cosine, and the imaginary component was the expansion for sine. He discovered this remarkable relationship known as Euler's formula. This formula is fascinating as it forms a relationship between Euler's number, the imaginary number, and the trigonometric ratios. From this, if we substitute x as pi, we know that cos pi is -1 and sin pi is 0. And by simplifying this out, we are left with Euler's identity. There is an undeniable beauty in the proof of Euler's identity, as it reveals a relationship between these seemingly unrelated mathematical concepts. It weaves together Euler's number, the number that arises from compound interest, the imaginary number, the square root of -1, and pi, the irrational number found from the properties of circles. However, the beauty of Euler's identity isn't just found in its proof, but in the timeline it represents. It is a collaboration of people all over the world across thousands of years, from the very first ancient number systems to the birth of modern calculus. And it all started 40,000 years ago at the very dawn of human civilization.